Relative velocity, type 6 collisions. So collisions doesn't really come up too often in the exams. I suppose it's come up a little bit more often in recent years. But when we're looking at collisions, generally what we want to do is show that two things are on a collision course. Then we want to show that the relative position of one relative to the other is equal to minus constant times the velocity of B relative to A. So in this case here, we have to show that the particles collide. What we'll be looking to do is get the relative position of, I think we're looking for B relative to A in this case. So again, always checking which way we're to do it. And then it'll be a constant times the velocity, where the velocity, or the constant will be a negative value. So for the first part of the question, however, we're just looking for finding the velocity of B relative to A. So that means I need the velocity of B minus the velocity of A. And of course, this is in terms of I and J, which is page 50 in our maths tables. So we know that we have two particles initially starting from points with position vectors respectively. Okay, so our position vectors is our or, and then we have our velocity vectors. So we're looking for the velocity of B relative to A, so we have to make sure we're using the correct vectors there. So we have our velocity of A is given by 4I minus 3J, and the velocity of B is 5I minus 7J, and we weren't given any units in that case, okay? So to get the velocity of B relative to A, we have 5I minus 7J minus 4I minus 3J. So taking like with like, so I's with I's and J's with J's, we have 5I minus 4I, leaves us with just I, and then we have minus 7J minus 3J. So minus 7J plus 3J gives us then minus 4J. So of course we need our magnitude and our direction. So it doesn't ask for it, but we should always work out our magnitude and our direction. So our magnitude, so is our absolute value. So it's our A squared plus our B squared. And that's the square root of 1 squared plus minus 4 squared, which gives us root 17. And then our magnitude will be important because obviously if we're looking at are they going to collide or not, then we need to know its direction of the relative path. Are they on a collision course or not, based on where one is with respect to the other. So of course, to get tan, it's J over I, or opposite over our adjacent, and our J is 4 over 1. So theta is equal to, I can see it's positive I and negative J, so that means it's going in east direction, 75.96 degrees, and then the negative direction means it's going south. So this direction is really important for collisions. In other words, what's their slope? So that's the magnitude and our direction. Okay, so we then want to show that the particles collide. So to look at the particles collision, we need to look at the position vector. And of course, the position vector is going to be or B minus or A. And again, this is also on page 50 of our tables, our relative displacement. Now they use S in your maths tables. So S of, what do they call it? S of B relative to C is what's in your tables, but it's the same thing, okay? So in your book it tends to use or, so we'll stick with the or. So of course, what's our position vector for A? Well, if we go back, it said the position vector for A was 6i minus 14j, and the position vector for B, well, that was 3i minus 2j. So the position vector of B relative to A is 3i minus 2j minus 6i minus 14j. So again, if we take like with like, we have 3i minus 6j, which is, or 3i minus 6i, I should say, and minus 2j minus 14j, so that gives us plus 12j there. So of course, to see if they're on a collision course, we should have a constant that is common between the position vector and the velocity vector. And you can see minus 3 is common here. So if I take out minus 3, that leaves me with I minus 4j. And of course, if I go back, what do we notice? Well, we notice that the velocity vector was I minus 4j. So here we have a negative value in front of it. In other words, our displacement vector is equal to minus a constant times the velocity vector. And therefore they must be on the same collision course. Okay, but also just to back that up, we'll look at the slope. So our slope again is our opposite over adjacent. So we have 12 over 3 there, which is 4. And therefore tan inverse, I can see it's going west because it's minus 3i. And then plus j, which means it's going up, so north. So therefore we can see they're definitely on a collision course, because if we're looking at one relative to the other, well, the velocity, the direction in which it's heading is east and then south by the same angle, and the position vector is north and then, or west and then north. So they're exactly the same, heading for each other, and the distance between each other is exactly the same. So therefore they must be on a collision course. So in terms of marks, what had we got? Well, we had 5 for I minus 4j, so the velocity vector. And then for magnitude and direction, we were getting another 5 marks. And then for getting the position vector and also the slope, and comparing the two to prove and make our statement here that they must be on a collision course, we were getting another 10. So it was only a 20-mark question that year. It was very simple question, so not too many marks going for it. Okay.